So welcome back to the Mechanics Miniseries, and now we're on chapter 3. Oh, that is the worst M I've ever. Moments. You know when you change pens and then suddenly it goes from like something that takes quite a lot to write, and then this is very, very smooth. So it's just I've forgotten how writing works. But today we're going to be studying moments. So this is not just me having a breakdown for an hour. A moment is a thing. It is a quantity. It has a unit. We're going to look at how we compute them. And it is a mechanicsy thing, obviously. If it can go wrong, it will go wrong. Oh yeah, that's what we get with this. So as like a little, each of these streams can be watched in isolation. You don't need to go back and watch the other one. But just as a little aside, last time we looked at Newton's laws. And computing. So we looked at sort of you can see that says laws, right? It's fine. Yeah, so we looked at computing F equals ma. We looked at sort of resultant forces. So if you had like a body or a box, and we have loads of different forces on it. We looked at sort of what the so-called resultant force was. So we could take on a single object, on a point mass, if you have all of these forces moving through the object, kind of sum them and get the total force. Essentially, if force is a separate vector, how do we add all those vectors together to get the resultant, the overall effect? Okay, if something is pulled up and to the side, it's going to move in a diagonal direction. So that's where the resultant force is from. And we looked at things like friction and boxes sliding down inclined planes and light inextensible strings and rods and pulleys and all of the classical mechanicsy can't model the real world, so let's abstractify it down to a point. So typically when we do the above, we look at forces going through the center of mass. So and this by considering force through the center of mass. And that is because we essentially, if we model it at a point, the point is located where the center modeling. So in order to look at a box sliding down a plane, instead of a box, realistically, we have a point, but we draw a box so we can point at like the sides to realistically just draw the angles nicely. And if I was going to model a point, I just do like a tiny little dot. That's not really great for a diagram. So diagrams tend to be over exaggerating the thing that we're looking at. But what if instead things have volume? What if that's not one word, but it is now? Have volume. Well, then forces would be equal to. The word I want to say is force, and I'm like, that forces be force. Forces would be able to act at points, directions, not through the center. So now things can act not through the center of mass. And then how do we work out their effect? How do we deal with it? Okay. Which is essentially a lot of words to say that before we looked at rods, say we had a beam or a box, and we modeled it, instead of looking at this entire shape, modeled it as a particle. And we looked at forces that moved through the particle, rectify that down to just a point. But when things don't work through the center, so say now this said I push down sort of here, how do we deal with that? Because it's not moving through the center, so the force felt at that center mass is going to be different. Now I can do a sort of demonstration. Say my pen, center of mass is going to be about there. Say halfway, pretend it's uniform. Get a uniform pen, hold it in its center. If I apply a force to one of the ends, what's going to happen is it's going to turn. So when forces act on something not through the center, no, I'm just moving this up and down, but when forces act not through its center, it has a rotational component. So it adds some sort of like twisting motion. Causes the body to rotate about the center, or about a fixed point. I can also hold it here and apply a force, and it's about that fixed point. And this is what we call is a moment, is the effect of the force, rotational part of, say this in words. It's the moment of a force. There we go. So. Moment of a force. Measure effect. Oh no, I don't want to go to a new page. By force on a rigid body. Error in line 163. Coda only has 75 lines kind of day. It really do be. It really do be. Also, hello, welcome in. So, moments of forces. If there's no force, there's no moments. Measure of the turning effect. So the moment of a force moving through the center or through the point of rotation, because it has no effect. Since moments measure rotation, and our vectors, they have directions. So we need to specify. And because we're talking about rotation in particular, specify clockwise, anti-clockwise. And I don't know if anyone's seen Agatha All Along, but I want to talk about it for a moment. So if you really, really don't want any spoilers and you consider any topic of conversation about Agatha All Along to be a spoiler, disappear. And I'll stick my hand up when it's safe to come back or mute. I'm not going to talk about the plot I'm just going to talk about a reference that is made. So, yourself now. They make a reference to the fact that Gen Z don't know clockwise and anti-clockwise. Like, it's a joke. And I kind of get it in as much as, like, digital clocks are more common now. People have phones instead of, like, wristwatches, or they do have a wristwatch, normally a Fitbit. But I think I got a bit mind boggled to be like, there's no other place where really clockwise and anti-clockwise kind of comes in that a typical teen, late teen. And it just blew my mind. It just genuinely blew my mind. Safe to come back now. What direction does a vector point if it denotes rotation? The direction change time is the direction. So I'm being very like hand wavy when I say it's a vector here, but essentially a moment has a size and a direction. How I'm specifying vector. Technically, it will have like if we defined our vectors into polar coordinates, it would have some r component and some component that would around, but we're not doing circular motion for a while. So I just want to say, yeah, it has a size and it has a orientation, perhaps rather than direction. So it's either going clockwise or it's going anti. Relative unit vectors, baby. Exactly. So for everyone's benefit, clockwise is that way around, right? Spins in the positive clockwise, and then anti-clockwise going backwards. And it's all fun and games until someone says that you need to like screw something in clockwise, and then I always get confused. Like you're looking at it in terms of the screw or in terms of the point. But yeah. Okay, so moments, they have a size and they have a direction. And I'm going to tell you their units are Newton meters. Okay, write it NM. So if you were here, or if you have watched the video, because it's on YouTube, by the way, all of these are on YouTube. If you want many hours of me chatting nonsense, find them there. If you remember what we talked about with units, we can use our units to work out our equations, and we can use our equations to work out our units. So because it is here we have Newton meters. So we have that is a force. That is distance. Okay, newtons are a measure of force, and meters are a measure of distance. Unit of distance. And that's precisely the equation. So the Newton meter, so the moment, is force times its. Now with some like little apostrophe here, because specifically when we say distance, perpendicular between. Okay, so if we have a F and we have a point here, F is away, so then the distance that we care about, remember that force is a vector, so it has a size and a direction, but the direction is the same along the entire line, right? We're going to pretend that that is a straight line. The audio might keep cutting out. I think my mic is being awful to me. Sorry. So that force acts in the same direction all the way along. So what we want is the shortest distance between the point and the line. So if any of you do or are interested in vector calculus in a bit more detail or vector algebra in a bit more detail, there's a really nice proof, geometry actually as well, that the shortest distance between a point and a line is precisely the perpendicular. And you can think about triangles. If I do a line, say from down here up to the point, or I do a line from slightly closer in to the point, the one slightly closer in is going to be shorter. That top line is shorter. And actually that kind of keeps happening all the way to perpendicular, and then they start getting longer again. So what we want is the perpendicular distance. And by perpendicular, I mean they're at a right angle to each other. So the moment about P FD. And we have to specify here, we're saying positive. So I'm going to use this notation a lot. That symbol to mean that anti-clockwise here is positive. And why have I chosen that? Well, that's because F is moving in an anti-clockwise motion about P. If I imagine that I fix my point at P, say I'm at P, and I have a rope between me and the point at F, and it spins in the direction. Again, we're spinning to the left, which in my brain means that we're spinning anti-clockwise. We could have also defined it the other way, and then we would have worked out if clockwise was positive, this might be a negative force. Clockwise direction. Realistically, what we do is we compute all of the forces in the anti-clockwise. We compute all of the forces in the anti-clockwise direction, and we compute all of the forces in the clockwise direction. Or counterclockwise, as the Yanks say. Correct. Anti-clockwise and counterclockwise, same thing. Not clockwise. So yeah, that's how we do it. So we have to take the moment about a point. We can't just have, what is the moment of this force? That not enough information. Not enough information specified. Right, I missed some of that. Someone came across a new expansion when doing other stuff. Quantum field theory, terrifying. Principle moments be derived from Newton's, or is it its own law, law of lever? I had a confusion about this when learning it. I don't actually know the answer to that, so in the next break I'll go and have a key reference, check my books. I would assume it's its own thing, rather than being derived from Newton's laws, because it introduces sort of a new concept. But don't quote me on that. We have to define a norm. We're staying so far away from defining norms and metric spaces here, it's not even funny. But yeah, if we want to compute the moment about a point, force times distance, but perpendicular distance. So we're going to need to compute perpendicular distances a lot. And when we're talking about things moving through, I would call it anti-clockwise and pro-clockwise. Oh no, don't make me dab that. That's awful. Terrible. That is an option. That is an option that you can make with your life. So yeah, if we have another example of this, if we have a point P and we have a series of forces, let's say here, then what we need to do is find the perpendicular distance, so sort of extend them down at right angles, that one. Oh, and we're going to pretend that every line I draw is straight and beautiful and like definitely what I meant it to be. We don't line shame here. So as you can see, some of these forces are working in a clockwise direction and some of them are working in a counterclockwise direction. So there's a lot of force happening on this point. And essentially, just like when we add up forces acting through a body, we get this like resultant force when we do this, we're also going to get a resultant force, right? If you have two forces working in opposite directions, potentially the resultant force might be something like that, say. So the total force effect of this is going to be moving in the clockwise direction because it's 2 against 1. But it will depend on how far away the force is from something, and then also how much force is being applied. So from this equation, we know that the further away a force is from a point or felt, the bigger the moment. There's a whole spiel that we could do about torque, but we're not going to go into that just yet. But if you've ever tried like fighting with an Allen key or like a screwdriver that has a 90-degree angle, you know that the further away you hold it, the easier it's going to, or a wrench, the further away you hold it from the point of rotation, the easier it is to rotate. And again, we'll get onto that in, I was going to say episode 6, I mean lecture 6 or 7. I don't know. One of the later ones. So stick around. Haha. Teacher taught rotational motion analogical with linear motion, like making comparison. So on. Yeah, that's a really decent way of doing it. So they all have sort of comparable things, but it's good to hold them separately in your head as well because it can get confusing. Allen key is the L-shaped thing, right? Yeah. So it's sort of a hexagonal cylinder, but it has a 90-degree bend in it, and that well, normally a short end and a long end. I don't have one easy to hand, otherwise I would demonstrate. But essentially, it's this little L-shaped thing, and normally you have sort of the short end, and you put the long end in and rotate through that if you want. If it's sort of far away, or you'd want to do it quickly because it's easier to pivot. But normally the long lever is coming around. Did I know Allen is a brand name? No, I didn't. What's the? Oh, is that like a hex? Mad. Okay, it is a hex key. I don't. 0 out of 10. I like an Allen key. I don't want it to be. What if I ignore it? Okay, so the only thing we need to worry about now is, well, what do we do about centers of mass? It's a frisbee versus flat. Frisbee is a brand name? Oh, no, don't start spherical cows again. No, I refuse. I refuse. Scandalous. Nobody calls it that. Never heard it at Hex key outside discussion. So I have, like, I think specifically like on TV when there's been instances where someone's been like, "Oh, pass me a hex key." Same with Hoover as well. I knew that one. I think I would say vacuum. I think I'd call it a vacuum, but the action is hoovering. So who knows? Anyway, okay, so we're going to talk centers of mass. So for a uniform rod, form bodies. So specifically, a rod is has. So I'm going to do COM, center of mass, and it's going to be L over 2 down its body. So specifically, if the rod that, then centers of mass, or as I call them, cathedrals. Yes, very funny. It's going to be halfway down, right? So essentially, it's going to be for a uniform body that's nicely shaped. It's going to be in the middle because it's the center of all of the mass. And when it's a nice shape, a sphere has a center of mass at the origin inside. We don't have to worry about 3D shapes just yet. But we know that that distance there is L over 2. Like that distance there is L over 2. Okay? For anything... Thank you, I used a cheat. There's a tool that lets me draw squares. For a rectangular lamina, which is a perfectly thin 2D form shape, it is where the diagonals. And I think that that is true. So now we have a sort of rectangle shape. If I draw my diagonals in on my rectangle, then my center of mass precisely here. And in particular, if the full thing is the width, then that's going to be the width over 2. And that's going to be the length over 2. If that is the length, that is the width. Okay, so it's precisely in the middle of the shape. And there's a sort of more general rule that we really won't be looking at, but it's just good to know. Any general uniform laminas will have center of mass lying along lines of. So in this shape, the lines of symmetry are the perpendicular and vertical and horizontal cross. And it lies along both of those lines, specifically at the intersection of those lines. And that is precisely because when it's uniform, the mass is evenly distributed across the entire shape. So it has to be, if it was on one side, the shape wouldn't be symmetric. So it has to be on the line of symmetry. So where you have multiple lines of symmetry, their intersection where center of mass is. If it's a non-uniform shape, normally you're given everything else and you're asked to work out what where the center of mass is. Normally only with rods or one-dimensional. At this sort of level that we're looking at, we don't do anything. At the level we're looking at, yeah, we don't do anything more complicated than that. So I'm just going to BRB. That is better. I realized I was like, I'm going to stand up because I've been sat down all day. And then I realized that actually, no, I haven't been sat down all day. I've been stood up all day and I was getting tired. This also works for raising your hand. Can't even type on a keyboard. Would you like to raise your hand? Anything you would like to share with the class? Where is the center of mass of a donut? Not in the donut. So a perfect torus, a perfect center of mass, a perfect donut shape is in the middle. So the one plane of symmetry is half up, half down, right? If you think about it, it's a cylinder looped around. So at the halfway line, and then slap bang in the middle of hole at the center of the hole in the middle of the donut. So you have something that like looks like that, right? Where sort of that cross section there looks like this. And then the top down view sort of like that. Okay, so like looking top down. So yeah, horizontally, that one. Horizontally, my line of symmetry is precisely what I said, so it goes through all of this, lines sort of perfectly. So it has to be in line with that point as that loops around. There's this like point of symmetry looping around the torus, and then that loops the whole way around here. So everything is symmetric, everything is the same going all the way through that, which puts our center of mass precisely in the middle of that ring. By the experience to find an object whose center mass is actually outside of it. Yeah. I mean, if we go back to our, even just our rectangle, right? Actually, let's go to a square. So the square center of mass is at the point where these things intersect. So is right. And now if I, where did you go? Sorry. If I cut a hole out of this circle, out of this square that is perfectly spherical, annoyingly, it's not going to let me do it. Okay, might actually be better off not using the tool. If I cut out the hole that is, pretend, a perfect sphere around it, so I remove exactly the same mass in every direction, I haven't affected where the center of mass is, because it's still got the same amount of mass. Oh, is that true? Yeah, the lines of symmetry are the same. But the torus one is the coolest one. Definitely a much cooler answer. So yeah, if it says like you need to hang this object by its center of mass, it's can't. Very peculiar experience with a point of interest of an image actually outside said image. Yeah. Okay, we have an ad break coming up, and I could use a glass of water. So I'm going to want to BRB, and I don't go anywhere. There we go. So we have question 1 of our exam style questions. A beam is held at equilibrium, modeled as a uniform rod with a weight of W newtons and a length of 10 meters, held by light inextensible strings at points C and A. Given the tension in the string at C, twice the tension in the string at A, find the distance between points A and C. So first things first, whenever I do a question, is I draw it. So let's draw some things. It would help if I specified that the beam. So here is our point A. Here is our point B, our beam, and here is audio cutting out. That is annoying. So we have our beam AB, and we have our point C partway along it. We're asked to find, so let's put some things in. We have total length of this beam. Yeah, 10. And we're asked to find what this distance. So that is our D. 10 meters. This is so this is our information that we're given. We're also given that the tension here, so let's draw some forces in. So we have the tension here, twice the tension here. This tension is labeled T. This is going to be 2T. Okay? We're also given that the rod is uniform and it has a weight of W. So because it's a uniform rod, we know that halfway along it is going to be where the center of mass is located. So we know that that is going to be, it could be anywhere along. I'm going to assume for the moment that it's here. Okay. And we actually, it's W newtons, so we can just do W.
How has it
Let's
been
put our
that
units
long?
in. Thank you so much. 40! Bloody hell. That's a while. That is a while. So here, hello, welcome in. So here, the fact that it's a uniform rod means that the mass is even distributed throughout it. If it was non-uniform, we wouldn't be able to make that assumption. That's what that's telling us. That's telling us that we need to think about the fact that it's uniform means that we can guess. So in order to find here, we need to take moments on this. So we could take them about any of these points. I'm going to take moments about the center of mass because I can. Can I? Yeah. Oh, is this me cutting out? Oh, that is quite bad. Is that better? It might be potentially a bit worse, but say lots of words for a really long time. Supercalifragilisticexpialidocious, slanfapulquigicogarichudroppelclanticiliogogogoch, taumotafakatangi ko ao tamate turipukaka pikimara honunu kupok if anyone tanatahu. Whew, how is that? Okay, cool. I've essentially just turned all of the noise gate filtery stuff off, but we will make do. We will make do. So things other than symmetrical objects, you do it by dividing the point mass as an object which is applied. What is that? I said thing from Mary Poppins, a place in North Wales and a place in New Zealand. I have made somewhat of a meme of myself for saying on the internet a lot. So I got challenged by my New Zealand followers to learn the other one. I apologize for the butchering of the other one. That is my attempt at memorizing it. I'm sure I will get corrected if needed. How dare you? Also, supercalifragilisticexpialidocious isn't a place. It's a like feeling, right? Anyway, should we go back to maths? So we need to figure out the length d, so the distance between A and C here. So I'm going to take moments about A. So if we have our point A, so force through the point, we ignore, okay? We don't worry about that T moving upwards just yet. Instead, we have a force moving downwards here that has a distance 5 to a force W. And then we have some amount more. Actually going to do it this way. So I'm going to say that's A. That is W, and this distance is 5. and this is D, and this is 2t. Okay, we're told that it's in equilibrium. So it's in equilibrium, which means that the total moments are 0, i.e. the moments in the clockwise direction and the moments in the counterclockwise direction balance. So we have, if we look at the counterclockwise direction, so let's say clockwise is positive. So that means that we have, we just set them equal to each other, we don't even need to do that. So in the clockwise direction, we have 5 times W. And in the counterclockwise direction, it would help if I drew something different. In the counterclockwise direction, we have that D times 2t. And I realized I did 2 different types of multiplication there. So this gives us, we're slowly getting there. This gives us that 5W over 2t is equal to D. Yay, amazing. Except this has 2 values in it that are not helpful to us. So instead, what we can do is look at moments about C. Okay. So now taking moments about C. So we have no. You know what? Every time I'm like, I'm not gonna make a mistake this episode. I'm gonna do it properly. We don't. Instead of doing that, we're taking the Z, exactly. So we need simultaneous equations to solve this. And the reason that I'm pausing is because I drew that the center of mass was in between this length D. I assumed that D was bigger than 5. That could be wrong, and it could be over here. If it was over here, if the distance between A and C was like very, very close. No, she's right. She made a good assumption. Ha 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 ha. If anyone's wondered what a mathematician's mental breakdown looks like, this is it. My argument, okay, someone fact check me this. My argument is that the center of mass has to be between A and C in order for it to be in equilibrium. If the 2 points were something like this, yeah, if it was like this and this was A and this was C and this was the W and then this was B, if it was that, yes, she's having a moment, deal with it. If it was this, taking moments about W, there's no anti-clockwise moment to counterbalance the clockwise moments, which means that it wouldn't be in balance and it would be, I got the joke. God damn it, Cat. Has to be closer to the left string than the right string since the force is less. Yeah, I also agree, but just to validate my brain, it has to be in between the two as well, right? Because otherwise it's not in balance and it's gonna rotate. Which means, so reasoning. D center of mass must be between the 2 force strings so that it is held in equilibrium. The center of mass has to be closer to the left string than the right string since the force is less. It has to be closer to the right string because the moments balance. So because the force is big... Okay. So. Let's do this properly. So we have our rod. We have points A, C, B, and I call it D here. Here we experience some force upwards. Call it T. Here we experience some force upwards. We're going to call it 2T. We don't experience anything at B, and at D we have some force downwards. W. The question was, does C and D swap? Where is... was this the right assumption? And then the follow-up question is, how far away are the two? What's the distance between A and C? The first question comes from, or the first answer, where the weight, where the center of mass is, comes from the fact that we said it's in balance. If it was over here, for some reason, A and C were really close together and the center of mass was further to the right, then the total moment would have a positive spin on it. So it can't be there because we're told that there is no total. We're told it's in balance, which means that the moments clockwise have to match the moments anti-clockwise. Which means we can do the thing that I written in my notes that I initially did, that I was like, no, we can't do that. So we're going to do that. So we take moments about D. Okay? So because we know for a fact that it's halfway along the bar. So we know that the distance here is definitely 5. If anything, the question was where is C rather than where is D. And then we have that this is a length little d. So moments clockwise equal moments counterclockwise. So looking clockwise about D, what moves forwards? We have A, and it's A times 5, so T times 5. So we have 5T. Remember, force times distance. And then on the other side, we have however much this is as a distance. So we have D minus 5 times 2T, which we can now simplify. So cancel out the T's. We get 5 is 2D minus 10, which is 15 is 2D. So D is 7.5 meters, because we are good mathematicians and we make sure that we use our units. Whew, we got there in the end. That's the simpler question that I have written down. It took a while. That was my confusion. I need to back myself more. We can slowly go through the next one because I have it written down in much better detail. Don't be disparaged as well. Like, all of these equations are sick dab, bruh. All of these questions are from sort of an A-level style exam. So if you're in the UK, specifically looking Wales, England, and Northern Ireland, it's the optional exams you take 16 to 18 years of age. Different schooling systems do it slightly differently. So we are, you know, getting up there a bit with how complicated the question style, but I want to show you the sort of thing and then how we kind of work through these sorts of problems. Grateful. Thank you very much. Okay, next question. As with always, we're going to start with a diagram. Don't you worry. Hello. We have a uniform rod of mass M is supported by a hinge to a wall at one end A at a point C along the at point C along the rod, distance 3A away from A, a light inextensible string is attached, with its other end attached to a wall at point D. A distance 2A above A. At the far end of the rod at point B, a mass of M is attached. Given that the rod lies in equilibrium, how show that the tension in the string is... It would help if I could type properly, you know? Yes, so that is the question, and it does come with a diagram. And the diagram looks like this. So we have our... I didn't get an ad? Oh, weird. Who knows? Looks like this. So we have our point A, we have our point C, we have our point B, we have our point D. So here we have a rod attached to a wall. So this is our wall here. I'm using some fluid dynamics notation to just kind of add some hatching to it to kind of show that it's a wall. And that looks absolutely awful, so let's just get rid of that. So we have a wall, vertical wall, we have a horizontal rod, and we have our string attached to it. So applying some distances here, we're told that this distance here is 3A. This distance here is 2A. Are we told the length of the... We should be told the length of the rod. The distance here, sorry, finally, is A. So those are all of our lengths. We don't know how long the string is. We don't need to for the moment. And then we also have that there is force acting along the string here in tension. Then there is a reaction force at A moving into the wall. We also have that the mass of the rod is moving downwards through its center of mass. So the length of the rod is 4A, which makes the center of mass 2A along it. Okay. So this is what we have to work with. So the question is find T. So we have a series of we have two forces. Oh, there's also, thank you, perfect. There is also a mass attached at the end here, mg. So the mass at the end and the mass of the rod are the same. Just to add a bit of confusion into the system. So we have 2 points acting downwards. We have some tension acting at an angle. And we have the reaction force of the wall and the rod touching there. And presumably there's also some frictional coefficient holding it steady, but we don't care about that too much. So these are our forces. So the first thing I want to do is, because I want to talk about perpendicular moments, when we talk about moments, everything is very nicely working in line with the horizontal rod. So I want to try and figure out what this is, okay? So in order to do that, I need to look at the sort of triangle that we're making here. So I'm going to chuck an angle theta in here. So if I do that, if I say that that is my angle theta, then I have Oh no, I don't want to do that first. So I want to find out what that the vertical component of the tension. Okay, because I want to resolve the tension in the vertical. I can work out the length of the string because here I have a right angle triangle, and this is 3A and this is 2A. So we have that this length here, x is equal to the square root of 3A squared plus 2A squared. Squared. Trigonometric projections, yes. Don't want to mess up your question, but where does it say that CB is A? In my notes and not in not in the thing. Mass M, length 4A. It's like it was always there. Sorry. So we get A squared, so let's bring the A out, and then we get the square root of 9 plus 4. So we get that this length here is root 13A. So given that we're told to show that the tension is mg square root 13, we're already off to a good start. So here we have that this length is, I'm going to do it in orange, root 13a. So in order to find t, what I'm going to do is I'm going to take moments, and I'm going to take them about a, just so I don't have to worry about that frictional force. I'm going to about a. Remember that we're told it's in equilibrium. So in equilibrium, so we have that our anti-clockwise is equal to our clockwise, or clockwise is equal to anti-clockwise. In order to find t, I just need to put on the kettle. Yeah, exactly. So we can set them equal to each other. So looking at moments that work in the clockwise direction from A. Okay, so everything that pushes the rod sort of downwards from A. So we have a distance here. So the center of mass is 2A away from A. Gotta love the labeling. Times mg, which is our force downwards. And then we have a mass at the end of the rod, which is 4A. So the full length of the rod away, and again times mg. And that's going to be equal to our anti-clockwise moment. So now we know that this is the tension contribution is a distance 3A away. And that is 3A t, and then I want the vertical component, so it's sine of theta, where I'm just going to chuck theta there. Okay. So it's 3A sine theta. 3A the distance, t sine theta is the vertical component. Resolving this then, you get, this is 6A mg equals to 3A, and then we need sine of theta. So sine of theta is opposite over hypotenuse, so it's 2 over root 13a. So if you remember theta, we have opposite, adjacent, and hypotenuse. Sine is opposite over hypotenuse. Cos is adjacent over hypotenuse. And tan is opposite over adjacent. So we have our little SOHCAHTOA. It's not a mechanics lecture without trig. Who knew it? Bye bye. Have a good one. Look after yourself. We will be wrapping up shortly as well. Don't worry. So we have t, and then that was 2 over root 13. And technically this is a over a, but we're going to cancel through the a's.
We can actually cancel through the a's one more time because we have an a on both sides, and when we have a common factor on both sides, we can get rid of it. So we have 6mg is equals to 6 over root 13 t. Again, common factor, let's get rid of them. So we're left with t, multiply up by that root 13 is mg square root 13. So we showed what we were asked for. So if we write the question down properly the first time and we solve it, we can get to the answer that we needed to get. So we have the tension in the string here is mg root 13. So it scales. Crazy how it all cancels? Yeah. It's like it was made that way. Woo. Sorry, this music is making me silly. But yeah, so all we needed to do was take moments about a point and resolve, and because it's in equilibrium, if it was not in equilibrium, if it was moving, if it was being rotated, we wouldn't be able to do that. We'd have to deal with resultant moments and all that confusing stuff. So we have 10 minutes. We're going to see if we can get one more question in. It's a bit of a longer one. We'll see how we go. Now we have a ladder modeled as a uniform rod AB, has mass m and a length 6a. So let's draw this out. It rests against a smooth horizontal. That's not how you spell rail to start with. So we have our ladder AB resting so we have A and we have B. Rests against a smooth horizontal rail at C, and the rail is perpendicular to the plane of the ladder, so it's for all intents and purposes it's like a little dot. We have that the length of the ladder is 6a, and we have that this height above the ground is 4a. The ladder is included to the horizontal, inclined to the horizontal is what that's supposed to say, at an angle alpha, where sine of alpha is 4/5. And we have that there's a coefficient of friction, so a rough ground. So the coefficient of friction between the ladder and the ground is mu. It is in rest at limiting equilibrium. So going back to what we did last time in forces and Newton's laws, when we have friction, the frictional coefficient, when the two bodies aren't like sort of working against each other and there's no like effort to overcome motion, is 0. And then as it kind of pushes through, suddenly the friction coefficient gets more and more involved until some maximum coefficient, at which point anything beyond that, any force beyond that limiting equilibrium, that maximum friction coefficient it can feel, is going to slip. So if you ever watch something kind of like slowly slip and then just kind of fall, that's what's happening there, which is quite cool. So we have a load of things. Let's chuck some forces on this bad boy. So we have a reaction force working upwards in the ladder. We have a frictional force working against the direction of motion, which I'm going to assume is inwards. So we have F. And we have a reaction force where the ladder and the beam touch. We also have a mass working on the ladder here. So part A of this question is show that the magnitude of the force exerted on the ladder by the rail, which is this one here, is 9 mg over 25. Hence, or otherwise, but we're going to say hence, find the coefficient of friction. So we know a few different things. There are some things we don't know in this system. One of them is sort of what is, say, this distance here, which we might want to look at. And yeah, there are a lot of forces at play. So first thing we're asked is show the magnitude of the force exerted on the ladder by the rail is at C. So I'm actually going to cheat, and I'm going to say, what if we look, instead of in the vertical and horizontal, we look sort of in these directions. So like in line with the ladder. So if we were to do that, we still have A, we have C, and we have B. And now we have that the reaction force is perpendicular to the ladder. We have, at some point here, a contribution downwards and a contribution inwards. And here we have a contribution upwards and a contribution inwards of R. And then this is sort of mg mg cos alpha. This is mg sine alpha. There would also be some contribution of friction, and here we just have the reaction force. So the reaction force is nice and normal. The gravity we can split nice and normally, so we have cos theta and sine theta. The frictional forces at A are kind of gross, and we don't know that much about them. So the best way to get rid of, if there's one point in your system that has really, really gross stuff happening to it, we get rid of it. So in order to not deal with the forces at A, we take moments about A. So this is the trick. This is the sneaky thing, is just if there's a lot of forces happening at one specific point that we don't want to deal with, or if there's something about those forces we don't know, if we take moments about it, because we multiply by that distance, the distance is 0 from the point to itself. So we just get rid of it. We just ignore it. And it's all nice and shiny and much better. So, things we don't know. We know that the length, so length AB is 6A. We don't actually know what the length of AC is. This is where we use what do we use? We use similar triangles. Snazzy. So similar triangles are where we have this angle alpha, and we know that that side is 4A. We need this line X, and we know that the dashed line here is 6A, the whole thing, and we don't know what that is. Call it Y. So we know that sine of alpha is 4/5. Okay? But sine of alpha is also opposite over hypotenuse. So 4/5 is opposite over hypotenuse, but and we can plug those in, so we get 4/5 is 4A over X. Cross multiplying, we get 4X is 4, I'm going to change that around a bit, 5A, just so I can cancel out my 4's, and I get X is 5A. So this distance here, length AC, is 5A, which is nice and neat. We love that. We don't even need to worry about Y. We don't need to care about how high the end of the rod is, again, over the vertical. So that gives us our distances. We know all our forces. Let's compute them. So the moments about A, we know it's in equilibrium, so they're equal to each other. So looking clockwise first is our gravity term. So the distance here is half the length, 3A, times the force, mg. I care about my mood. So we have 3a times mg, which is equal to our counterclockwise moments, which is our force at C. So we know now that the distance is 5a. R. I'm going to call it R. We were solving for R. It's not mg, it's mg cos theta. There we go. Cos alpha. Let's do all of that bit again. Take it from the top. So, counterclockwise, clockwise moments. Distance halfway of the length is 3a, and we have mg cos alpha equal to, now we know that that distance is 5a times r. So one final thing to do, and those of you that really like Pythagoras and all of that stuff that he did will notice that if you have a right angle triangle where the hypotenuse is 5, the one side is 4, the other side is going to be 3. Fun fact, 3, 4, 5, Pythagorean triple. They make a nice right angle triangle where all of the side lengths are unit numbers, or integers as they're called. So we know that cos of alpha is, if this is our alpha, if this is our alpha, is adjacent over hypotenuse, so it's 3 over 5. So 3a mg times 3 over 5 is equal to 5a r. Rearranging this, you get 3 squared a mg over 5 squared a equal to r, or 9 over 25 mg equal to r. So that is precisely what it asked us to find way back here. Show that the magnitude of the force exerted on the ladder by the rail is 9 mg over 25. Ta-da! Second part of that question is then find the coefficient of friction. So now we do need to include the stuff at A. But now we can go back to looking at vertical and horizontal components. So let's do another diagram, because we can tidy up and just care about what we care about. So now we have our rod, we have our labeling. So we have A, some point that's C, and B. We have our forces, so now we know that this is 9 mg over 25. This is mg. We have, that's still some reaction force we don't know, and now we have our friction. Things to note is the friction force is the coefficient of friction times the reaction force times that normal force. But all we need to do now, oh yeah, and we also have our distances. So mg, our center of mass, is halfway up our length, so this is 3a. We know that the total distance A to C is 5, so this is going to be 2a, and that leaves us with this being A. 3, 5, 6. Yes. Delightful. Let's resolve our forces. So this is going back to the work we did in the Newton meter, the Newton's laws and forces lecture last time. So essentially we look at forces in the horizontal direction, so what's moving in the horizontal. So we have F moving in the positive, and in the negative we have a contribution from this 9 mg 25, so 9 mg over 25, and in the horizontal is sine of alpha. Remember, alpha is this angle here. That's it. Those are the only forces acting in the horizontal. In the vertical then, we have our reaction force at A. We also have, going upwards, the positive contribution of the 9 mg 25 cos alpha. And then in the negative, we have mg. Remembering that F is mu r, I can write this equation as mu r equal to, and sine of alpha is 4/5. So mu r is equal to 9 times 4, which is 36 mg, and 25 times 5 is 125. This equation then I can write as r is mg 1 minus 9 over 25 times cos of alpha, which is 3 over 5, which gets me, I believe the two equations are mu r is 36 mg over 125, and r equals mg 1 minus 27 over 125. So if r is equals to 98 mg over 125, mu r, so we plug that in, 98 mg over 125 is equals to 36 mg over 125. Right, I'm going to do a load of cancelling before I try and take that over. So both sides have m's, let's get rid of those. Both sides have g, let's get rid of those. What else? Both sides have 125. Yeet. Now we have 36 over 98. 36, they're both even, so we can divide them by 2. So 36 divided by 2 is 18. And 98 divided by 2 is 49. Yeah, sorry, this song, I don't know how to get it off this playlist. It's not my playlist. There we go. Okay, so all we're left with is 49 mu is 18, or mu is 18 over 49. So a sanity check here is that mu has to be between 0 and 1. So if we ended up with a number that was bigger than 1, we've done something wrong. Luckily, it's not too bad. It's not too bad. And that is the answer I have written down. So that is pretty snazzy. So fundamentals to take away from this are the fact that if you're doing moments, a moment is a measure of the rotational component or the rotational effect that a force has on a point. In particular, when you talk about things that have distance away from centers of mass, they can be important, and especially when we're talking classic examples are ladders slipping down walls, or frictions, or things being held by strings. You also have their units are Newton meters or Nm, because they are precisely, the moment is the force times the distance, and specifically it's the perpendicular distance between the force and the point, which also is the shortest distance between a given line and a point is its perpendicular distance. Fun fact. You can still get resultant force moments in the same way you get resultant forces by taking the sum of them. So if the sum of clockwise and anti-clockwise moments is 0, it's in equilibrium, it's not going to move. But if it's not, then it has some rotational movement going on. For uniform bodies, centers of mass lie in the middle of the mass, which, if it is uniform and nicely shaped, will be where the diagonals cross, or where lines of symmetry. So if you have two or more lines of symmetry, it's where those lines of symmetry intersect. And that's because if it wasn't, then it wouldn't be uniform, because the weight would be more unevenly distributed in one half than the other. Fun fact, the center of mass of a torus is in the middle, so outside of the body. So the center of mass of a donut isn't in the donut, which is quite cool. And then we did some exam style questions. So rods being held by strings, rods being held against walls with light inextensible strings, basically lots of tension, lots of moments about awkward points, and then we finally did the iconic ladder leaning against something and watching how it slips. This is a classic sort of interview style question, exam style question. Fun thing to think about would be kind of resolving it, and then depending on whether the floor or the wall was frictioned, Are the moments resolved in such a way that the ladder could actually slide up the wall? And what system would you have to have in order for that to be the case? Normally we think about things sliding and they fall flat to the floor. But potentially there's a space where the ladder actually slides upwards. Leave you with that one.